Okay, here we go. All right, can I get a thumbs up at home that you hear me and see the board okay? All right, here we go. All right, so guys, section 2 starts a very, very, very important topic. It's the unit circle. However, I'm not even going to show you the unit circle yet. The unit circle will be a tool that we will use to help us find special trig ratios. At the end of the day, that's what the unit circle does. The unit circle also helps us redefine trig ratios so that they can apply to angles of any size. Because right now, I'm getting a little ahead of myself, the trig functions only apply to angles that fit inside of a right triangle. So you have to be less than 90 degrees. But we would like to be able to take the sine, the cosine, or tangent of an angle of any size. So by taking it to the coordinate plane with a circle, we are able to redefine the trig functions to do this. And technically I say redefine, but if you research this, these ratios, the new ones, existed before the SOHCAHTOA that you knew. So trig was originally defined the way I'm about to redefine it for you, not the O, H, and A that you guys are so used to. All right, but I am getting ahead of myself. I'm gonna go over here so I can move this up and down. But basically, we have a right triangle with an angle, and then based off of that angle theta, you have an opposite side, an adjacent side, and obviously a hypotenuse is always directly across from the right angle. The 6 trigonometric functions, as you know them, are sine, cosine, and tangent, and then their reciprocal trig functions are cosecant, secant, and cotangent, all right? So you already know this, good old SOHCAHTOA. Each trig function relates the measure of an angle to the ratio of 2 different side lengths. So for example, the sine function says the sine of an angle is equal to the ratio of O over H. So this function means in order to create an angle the size of angle theta, then there must be a certain side length ratio between the opposite and hypotenuse side. So guys, if you change the ratio between O and H from, let's say, 2 to 3 to 2 to 5, then you automatically change the size of angle theta, because the trigonometric functions literally say that the size of an angle is dependent on a side length ratio, okay? Move it up. So by their definitions, as you know them, SOHCAHTOA, the trig functions are functions of an angle. An angle goes into each trig function, and then a ratio of 2 side lengths come out. So the angle goes in, the ratio comes out. So anytime we try to graph a trig function, it is an angle that will represent the x-coordinate, and it is a ratio that will represent the y-coordinate on the graph of sine, cosine, or tangent, okay? The current definitions, as you know them, of these trig functions, they mean we can use angles that fit inside of a right triangle as theta, right? Because if you're going to use a right triangle, angle theta has to be smaller than 90 degrees, just based off of all of the angles adding up to 180. This one's already 90, so those two have to cut 90 in half. They have to be positive acute angles. So right now, your trig functions, you can only use trig on positive acute angles. We don't want to do that though. The goal in chapter 6 is to take trigonometry to the coordinate plane and apply the trig functions to angles of any size. So right now, technically, you should only be able to take the sine of a 58-degree angle, or the cosine of a 63-degree angle, an angle smaller than 90. We want to be able to take the trig functions of angles of any size. So I want to be able to take the sine of an angle that's 130 degrees, but 130 doesn't fit inside a right triangle. So, where am I? So not just angles that fit inside a right triangle. In order to do this, in order to take the sine of 130 degrees, we're going to redefine the trig functions using a point on a circle's radius, an x-coordinate, a y-coordinate, and a reference angle. So the O, H, A, H, O, and A that you guys all know and love is all going to change. And it's going to become a y-coordinate over a radius, an x-coordinate over a radius, a y-coordinate over an x-coordinate. So all of these trig functions are going to get redefined with a new definition so that we can apply it to an angle of any size. And that's the goal of the unit circle. It's literally how we come up with this relationship between the y, the r, and the x, all right? So the unit circle is going to show us all that. However, before we can do that, you got to know what a reference angle is. And our book, I think, does a terrible job of showing you that and then them just assuming you know what it is from Algebra 2. So today, I just want to talk about reference angles, okay? And I'm not even going to give you homework on it. So I just want to go over a few things, show you some reference angles, work with some radians, get comfortable, and then that's it. And then we'll ease into section 2 a little bit more tomorrow. All right, so let's go to, technically, page 2 would be this. This one. Okay, so in a nutshell, I'm trying not to get too far ahead of myself with the unit circle. The way we redefine these trig functions is take a circle, take an angle. This angle is obviously bigger than 90 degrees, right? But this angle, from here to here, it meets the circle right there at some point. Call it negative x and y, right? And then it clearly, from here to here, is known as the radius of the circle. So all of that is going to be used to redefine what the sine, cosine, and tangent of this angle is, so that I can take the sine of 130 degrees, not just a small angle that's less than 90. Okay, what happens is if you construct a right triangle, it's not your angle that actually fits inside of the right triangle. It's what we call the reference angle, the leftover in between your angle and the x-axis, okay? So we do have to be able to look and see, well, all right, I'm taking the sine of 130 degrees, but really, what's the reference angle? What's the angle that would have fit into a right triangle if I wanted to apply this to right triangle trig? So it's always going to be this reference angle, because what happens is, if you reflect this, because circles are symmetric in every direction, you actually end up with that reference angle in quadrant 1 as a positive acute angle. So you really do have this positive acute angle living inside of a triangle in quadrant 1. And then all of its points are symmetric to the other side, all of the values, the x, the y, and the radius. So that's basically what's going to happen when we redefine the trig ratios. And I'll redefine them all tomorrow. All I need you guys to worry about is, well, what's that reference angle? What's really the angle that would have fit into the right triangle, okay? All right, so a reference angle is a positive acute angle between the terminal side of an angle and the x-axis. So guys, this is so easy. Just watch how easy this is going to be. Again, I don't want to move anything up too fast in case you're writing anything down. All right, so I want you to find each reference angle. So guys, let's do 130, right? So I think the easiest thing to do when you're asked to find a reference angle is be visual, draw it. 130 degrees is going to land somewhere in quadrant 2, right? It's not going to go all the way to here at 180. So there's 130 degrees. The reference angle is always the leftover angle between the terminal side of your angle and the x-axis. So this distance right here is the reference angle theta. Well, guys, if this is 180 degrees and this is 130 degrees, how many degrees live in between there? 50 degrees. So the reference angle theta is 50 degrees. So when we start taking the sines and cosines and tangents of 130 degrees, I kind of think of it as, well, in reality, what you're doing, you're taking the sine or cosine or tangent of a 50-degree angle, but it landed in quadrant 2. It's not a 50-degree angle that landed in quadrant 1. All right, so it's all about that leftover, that reference angle that we would use to redefine these trig functions, okay? So you just gotta know what the reference angle is. Now, the biggest mistake I see with reference angles is some students go, oh, well, this is 90, that's 130, so it's 40. Guys, the reference angle never goes to the y-axis. It's always your angle to x-axis, no matter where it's located. Your angle to x-axis. All right, so what about 330 degrees? What's the reference angle to 330 degrees? So where's 330 degrees going to land? All the way in quadrant 4. So the reference angle is the angle in between your angle's terminal side, your ending angle, and the x-axis. So guys, that distance right there is your reference angle. Well, all the way around a circle is 360 degrees. So if that made it to 330, how many degrees live in between? 30 degrees. So the reference angle is 30 degrees, which is one of our specials, so he's a good guy. All right, so again, I don't mean to make this overcomplicated. It should feel extremely simple. It's just that leftover angle. All right, now the key thing about a reference angle, guys, is it has to be positive and it has to be acute. It has to be less than 90 degrees. So if they ask you what's the reference angle to negative 135 degrees, well, let's draw it. Remember, if you want to create a negative angle, you have to rotate clockwise from the positive x-axis. So now this is negative 90. I'll go a little bit past it. There is negative 135 degrees. So if I rotate it all the way to the negative x-axis, that's negative 180 degrees. So the reference angle is the angle in between your angle ending and the x-axis. So this angle right here is your reference angle. So how many degrees live in between negative 135 and negative 180? Technically, go ahead, Michael. It's negative 45 degrees. You're totally right. But is the reference angle supposed to be negative? No. The reference angle is supposed to be the angle that you could have put inside of a right triangle. So you just don't make it negative. It's negative 45 degrees, but we're just going to say 45 degrees. Okay? So again, I hope this is really simple. Now we get to 48 degrees. So guys, if you think about 48 degrees, a reference angle is supposed to be a positive acute angle. Pretty sure 48 is a positive acute angle. So when you draw 48 degrees, he's just hanging out in quadrant 1, somewhere between 0 and 90. So if the reference angle is the angle in between your angle ending and the x-axis, it's the exact same angle. So any positive angle between 0 and 90 is going to be its own reference angle because it already fits inside of a right triangle. So the reference angle is himself 48 degrees. All right, and then the last one, negative 59 degrees. Negative 59 degrees would land right about there in quadrant 4. So the reference angle is supposed to be the angle between your angle ending and the x-axis. So it's the same angle, except is the reference angle allowed to be negative? No. So the reference angle would just be positive 59 degrees. So in the future, if I'm ever asked to take the cosine of negative 59 degrees, I just think of it as you're really taking the cosine of a 59 degree angle, but it landed in quadrant 4, not quadrant 1. BB3. Hey, what's going on? Good, how are you? She's here. Okay, is there anybody I can send her now? Okay, great. All right, thank you. Bye. Ella, at the end, you have to fill a COVID form out?
I can't put it to in the bucket.
Okay.
At the beginning of the day.
I told him I'm keeping you anyway, but if you have to go at the end, we'll send you down. All right? All right, so perfect. All right, now, so the hardest thing usually about today is we got to figure out where the hell are these reference angles in radians. All right, so let's go and look at radians now. Okay. So if you're asked, what's the reference angle to 2 pi over 3 radians? Now, normally the rule is if you are working in pi's over 3, then your reference angle will be some version of pi over 3. If you're working with pi's over 4, your reference angle will be some version of pi over 4. But how many pi's over 4? How many pi's over 3? Now again, I tried telling you guys to think of this as 2 pi's over 3. pi over 3 is 180 divided by 3. That's 2 times 60. That's 120 degrees. 2 pi over 3 is 120 degrees. But I don't want you guys having to sit there all the time and trying to figure out, well, what is it in degrees? And then I'll figure out where degrees is, and then I'll go from there. Because if the measurement is given to you in radians, then your reference angle has to be given back in radians. So if you convert it to degrees, find your reference angle in degrees, then you got to convert that back to radians. It's like, wait, what? So I want you guys to get really good at knowing where 2 pi over 3 radians is. Where's 5 pi over 4 radians? Where's 11 pi over 6 radians? So if you go to that other page of notes, the anchors I called it, guys, I will never forget the day my pre-calc teacher taught me my anchors, and I use it to this day. Now, maybe last year somebody already showed you this, but I'm telling you, the anchors have been so crucial for me and radians getting along. All right? So if you could just go to your anchors before I do this problem, let me show you what I do. All right, so to save time, I filled in your anchors for the 45, the pi over 4, and the pi over 3, the 60. I'm going to do the 30 with you, all right? So this is what I think of it as. We know all the way around the circle is 2 pi radians. And we know halfway around the circle is pi radians, 180 degrees. We know that. Those are your anchors, okay? So if we're going to work with a 30 degree, that's pi over 6s. So when I'm working with pi's over 6, I think this. If I know from 0 to 180 is pi radians, then I say to myself, well, how many pi's over 6 would make pi? How many pi's over 6 would you need to get to pi? You would need 6, because the 6's would cancel, and you'd be left with pi radians. So to me, I always remember, that's where 6 pi's over 6 live. So when you guys are asked, oh, what's the reference angle to 5 pi over 6? Well, if this is where 6 pi's over 6 live, guess where 5 live? In the quadrant before. And now you know 5 pi over 6 is in quadrant 2. If you're asked, oh, well, what's the reference angle to 7 pi's over 6? Well, if this is where 6 pi's over 6 live, guess where the next one lives? Right here. 7 pi's over 6 are in quadrant 3. All right? And it also means that every 6 pi's over 6, you create half a circle. So if I go another 6 pi over 6 all the way around, how many pi's over 6 make 2 pi? 12. You would need 12 pi's over 6 to get all the way around, right? If this took 6, 6 more, 6 plus 6, you got 12. So when you're asked, what's the reference angle to 11 pi's over 6? Well, if this is where 12 pi's over 6 live, guess where 11 live? In the quadrant right before it. If you're asked, what's the reference angle to 13 pi's over 6? Well, if 12 pi's over 6 live right there, guess where 13 lives? In quadrant 1, in the quadrant right after. So I always use my anchors to figure out where the next one would be. So guys, go another 6 pi's over 6. From 12 pi's over 6, another 6. Now I'm sitting at 18 pi's over 6. Remember, because you can just keep rotating around. So now, if you were ever asked, what's the reference angle to 17 pi's over 6? Well, if this is where 18 pi's over 6 live, 17's in quadrant 2, in the quadrant right before it. If you're ever asked, what's the reference angle to 19 pi's over 6? Well, if this is where 18 pi's over 6 live on this line, then 19 live in the quadrant right after it. And then if you're sitting at 18 pi's over 6, right? Guys, go another 6 pi's over 6. That's going to land on 24 pi's over 6. So if you're ever asked, what's the reference angle to 23 pi's over 6? Guess where 23 pi's over 6 land? In the quadrant right before it. If you're ever asked, what's the reference angle to 25 pi's over 6? Guess where 25 pi's over 6 live? In the quadrant right after it. So remember, every pi radians is a half a circle. So 1 pi is pi. Another pi is 2 pi. Another pi is 3 pi's. What's 18 divided by 3? That's 3 pi's. Another pi is 4 pi's. What's 24 pi over 6? It's 4 pi's. So you can always count it like that. Does that make sense? Your anchors, if you will. So I call my anchors, how many pi's over 6 make pi? 6 pi's over 6. How many pi's over 6 make 2 pi? 12 pi over 6. And then you can just keep adding 6 pi's over 6 to create more rotations. All right, so same thing. My anchors for my 45s are 4 pi over 4 an 8 pi over 4 because that's where 3 pi's over 4 would be, and this is where 5 pi's over 4 would be. If this is 8 pi's over 4, this is where 7 live, and this is where 9 live, and so on. All right, let's go back to our radians now, and hopefully we'll be able to place our angles very quickly. All right, so here we go, guys. If I want to know the reference angle, the 2 pi's over 3, right? I got pi, and I got 2 pi. How many pi's over 3 make pi? 3 pi's over 3. Well, guess what? Where are 2 pi's over 3 then? In the quadrant right before it. So 2 pi's over 3 go to right there. The reference angle is the angle in between your angle ending and the x-axis. So right there. So guys, how many pi's over 3 live in between 3 pi over 3 and 2 pi over 3? 1 pi over 3 is your reference angle. And it's a positive acute angle because that's 60 degrees. All right, what's the reference angle to 5 pi's over 4? Well, in the world of pi's over 4, here's 4 of them. And then all the way around to 2 pi, here's 8 of them. So where would 5 pi's over 4 be? Well, guys, if this is 4 pi over 4, 5 pi over 4 is in the quadrant right after it. So 5 pi over 4 goes right there and lands in quadrant 3. So the reference angle is the positive acute angle between your angle ending and the x-axis. So this distance right here. So guys, how many pi's over 4 live in between 5 and 4 of them? 1 pi over 4. So the reference angle is 1 pi over 4. All right. What's the reference angle to 11 pi's over 6? Where do 11 pi's over 6 live? Well, guys, in the world of pi's over 6, 6 of them make pi, and 12 of them make 2 pi. So where's 11 of them going to be? Well, if this is where 12 pi's over 6 land, the 11th one will be right in the quadrant before it. So 11 pi's over 6 land in quadrant 4. And your reference angle is going to be the angle in between your angle ending and the positive x-axis there. So it'll be right there. So how many pi's over 6 live in between 12 and 11? 1. So 1 pi over 6 is your reference angle. Now again, you could say, well, hey, Hardy, it looks like it's always 1 pi over 4 and 1 pi over 3 and 1 pi over 6. You're right, probably it's going to be. But you got to know what quadrant you're in. Quadrants play a huge part. So you got to know where it lands. All right, and then the last one is 10 pi's over 3. What's the reference angle to 10 pi over 3? Well, guys, where do pi's over 3, where are your anchors? If I'm working with pi's over 3, 3 of them make pi, and 6 of them make 2 pi. Well, guys, I got to get to 10. So remember, every 3 pi's over 3 is a half a rotation. So go another 3 pi's over 3 from 6. Here's 9 pi's over 3. If you went another 3, that would be 12 pi's over 3. Well, guys, here's 9 pi over 3. So where's 10 pi over 3 going to be? In the quadrant right after it. So technically you did this. You went all the way around, and then you went again until you got to an angle that landed in quadrant 3. So here's 10 pi's over 3. Your reference angle, no matter how many times you rotate around, is still the angle in between your angle ending and the x-axis. So it's right there. So how many pi's over 3 land in between 9 and 10? 1. So the reference angle is pi over 3, but you're in quadrant 3. That's important. All right? So again, reference angles. Are they easy? Yes. Do radians make them harder? I'm sure. But I'm telling you, I will never forget my anchors. It always makes it easier than me trying to figure out, all right, 11 30-degree angles, my reference angles is this, and then trying to convert back to radians. Okay? I should have done a negative one, but guys, then it would just be, well, if you're going in the negative direction, then this would be negative 3 pi's over 3 and so on. So you still count it the same way. Go ahead.
For letter H, you went back with that's theta, right?
Theta is from here to there.
Okay.
Because in order to get to 10 pi's over 3, it takes more than one rotation.
Oh,
So I rotated all the way around once, and I only got me to 6 pi's over 3. If I rotated to here, that got me to 9 pi's over 3. It takes a rotation and another almost 3/4 to get into that 10 pi over 3. Okay? Yes, question.
Why is there not 2 pi after on the last one that we just did?
Say it again. Why is there not what?
Yeah, instead of 2 pi, why is there 6 over 3? But that is 2 pi. Never mind.
That is 2 pi, right? Yeah, because it takes 6 pi's over 3 to make 2 pi. Yep. Whatever you should put here, your first rotation, this should equal 2 pi's. Okay, those are your anchors. All right, are you guys okay? It makes sense? You're going to be able to find where your radians are. We're going to be all right? Okay. At home, can I get a thumbs up if you're okay? Awesome. All right, so guys, that's all I wanted to go over today was just basically a little bit of a start, kind of showing you what the gist is, and then knowing these reference angles. So I didn't even make a homework, guys. There isn't actually homework problems just on this, so I didn't want to assign anything else. So we will enjoy it on Monday, and we will pick it back up tomorrow. Guys, I take this section slow, because like I said, it's crucial to how we work with trade in the future, okay? All right, I have to take attendance really quick, but if I say your name, if you don't have any questions, you'll be free to go. And if you do, as always, please feel free to stay on the meet and ask me any questions.